Okay, so in this video, we're going to introduce uh, a new topic. So let's start with a little bit of motivation. So let's suppose we have a particle traveling through space, and now this particle is not just going to be traveling in one direction. Okay, so as time increases, our particle is going to be traveling in this direction. So really what we can think about is every point here at this point x, y, is really going to depend on one thing. So x is going to be a function of t, and y is going to be a function of t. Okay, so clearly this curve c that we have here, c cannot be defined as y equals f of x. Okay, so why can we say that y is not equal to f of x? Well, it fails the vertical line test. Okay, so this is where we have something new here that we can use. And so x and y are defined in terms of a third variable, and this third variable we call t, as we did here. And t is called a parameter. Okay, so t is called a parameter. Okay, so the way we typically write a parametric curve is we'll say c is defined to be x is some x of t, y is some y of t, and then we may or may not say t goes between some initial time and some terminal time. So t0 is called the initial time, or the initial point. The initial the initial time where x of t0, y of t0 is called the initial point. Okay, so definition. And t1 is the terminal time. And x of t1, y of t1 is called the terminal time, or terminal point. Okay, again, definition. Okay, and t is called a parameter. Okay, so why would we want to view parameters? Well, uh, thinking about when we can look at different particles traveling in now 2 dimensions, as opposed to everything else we have done in Calculus 1 and Calculus 2 has been motion in a single dimension. Now we're able to scale that up to add a whole nother dimension. Okay, so let's think about the following example. Okay, and this is more or less going to be a standard example I like to use a lot. Okay, so our parametric curve is going to be defined by x of t is equal to cosine t. Y of t is equal to sine t. And we're going to let t go from 0 to 2 pi, and we usually include the 0 but not the 2 pi. Okay, so if we were to plot this, let's plot it right over here. Okay, when t is 0, cosine of 0 is 1, sine of 0 is 0. So we're going to be right here. Okay, and what we're going to get is not something so straight. Okay, so you can pretend that this is a circle. This is in fact going to be a perfect circle of radius 1. Okay, so this is radius 1. Okay, so a few things when drawing parametric curves. Note we have to have an orientation. Okay, so why did I include this little arrow here on my graph? I include this little arrow on the graph so that way I know that the curve is moving around counterclockwise. Okay, so if I were to switch sine and cosine here, or replace cosine with minus cosine, I end up with the exact same curve. It's just going to be oriented counterclockwise, or oriented clockwise instead of counterclockwise. Okay, we can change our circle ever so slightly to come up with a slightly different example, or make it slightly more complicated. If we were to change this to now x of t is equal to r cosine t plus h, y of t is equal to r sine t plus k, and we'll still go from t between 0 and 2 pi. This is now a circle oriented counterclockwise. Of radius r, centered at hk. Okay, and what we'll see in the next video is we'll see that there is in fact a way to go back and forth, or to change our parametric equations to something we're used to working with in terms of y equaling f of x. Thank you.